Hi folks, welcome to our review for the midterm in pre-calculus. We're going to be reviewing quite a wide variety of topics and I want to make sure I touch on all those, but as always, if you have questions, the main reason I'm here is if you have questions, there's a chat box over on the right hand side. Please ask those questions along the way. So we're going to be touching on quite a few formulas and things like that. So just to keep in mind, if you have any questions, whether it might be generating the formula or things of that nature, or how a problem's worked out, please ask those questions. That's what I'm here for. So without further ado, we'll get started. So we want to find the midpoint. So we'll find the midpoint of the points 710 and negative 5, 4, and determine the distance from each of these points to the midpoint. So there's going to be two parts to this problem. Part one is finding the midpoint, and that's what we're going to start with. So in order to do that, we need a midpoint formula. And so the midpoint formula, you might want to write this down in your notes. If you have 2 points, let's say A1, B1 and A2, B2, then the midpoint should equal, well, you take the average of the first two x coordinates, so that's just, you add them up and you divide by 2, and then you do the same thing for the second 2 coordinates, so you add those up and divide by 2. And so that should hopefully be the halfway point. Now, does it matter which term you call A1, which term you call B1? No, not whatsoever. So, or A1, B1, excuse me there. Yes, that does matter. The A1, B1 does matter, but which one you call A1, B1 and which one you call A2, B2, that will not make a difference whatsoever. So you can have choices. In the case that we have here, we have 710 and negative 5, 4. And so just for simplicity's sake, we'll go A1, B1 right there, and we'll go A2, B2 right here. So when you do this, actually, and the reason why you can change the order, because you have addition up in that numerator, and addition commutes, so you don't have to worry about that whatsoever. So what we're looking at here for the midpoint equals, so let me abbreviate that right there, midpoint equals, so in our case we have 7 plus negative 5 divided by 2, and then we have 10 plus 4 divided by 2. And so that should make 2 over 2, which is 1, and our second point will be 14 over 2, which is 7. So that's the first part. And then the second part asks about the distance from each of these points to the midpoint. Now, if it's a true midpoint, the distance should be the same, and that's what I'm going to try and show here. Here's another formula that you might want to write down for yourself. It's the distance formula. And all this comes from is just basically the Pythagorean theorem is how you show this. And so for the distance formula, if you have, once again, 2 points, A1, B1, and A2, B2, and sometimes you might see x1, y1, x2, y2. It really doesn't matter in terms of what the symbols are, as long as you identify which are the x coordinates, which are the y's. So this formula is basically Pythagorean's theorem at work. So you subtract the 2 x coordinates, and then you add that to subtracting the 2 y coordinates. Now you might be concerned in terms of order here. As long as you're grouping the x terms together and you're taking that difference, and you're grouping the y terms together and taking that difference, you'll always get that distance to be correct, as long as you have those x terms subtracted in order and then you're squaring that. Because when we square it, it's going to turn positive anyway, so it doesn't matter if it's negative or positive inside this term right here and this term right here. So that's why we can kind of get away. We can be a little bit more sloppy than, say, when we're dealing with lines and things of that nature. So in this case, if we want to find the distance from the midpoint, so first we'll do distance from 1, 7 to, let's say, 710. And so this distance equals the square root. Notice our two x coordinates first, so we'll go 1 and 7. As I said, it doesn't really matter what order you choose them in, so we go 1 minus 7 squared plus, and then our two y coordinates, so we have 7 and 10, and we take 7 minus 10, the quantity squared, and then all we need to do is figure out what those values are. Well, 1 minus 7 is negative 6, but when we square that we get 36. So you get the square root of 36 plus another 3 squared. So this is 36, and this is 9. So that makes, that's a 36 there. And so that makes the square root of 45. Okay? So I don't see any questions thus far, so we'll keep on chugging along. And so now we need to find the distance from the midpoint to the other point. And if things go correctly, so distance from 1, 7 to negative 5, 4, if things work out right, we should have that this should be the same value. So distance equals square root of, and then notice we have a 1 and a negative 5, so we go 1 minus, and make sure you put in parentheses that negative 5, and we square that. And then we have 7 and 4, so then it goes plus 7 minus 4, the quantity squared. And so notice this is 1 plus 5 essentially, which makes 6, and we square that, we get 36. And 7 minus 4 is 3, so we get 9 there. So this thing equals the square root of 45 as well. And so we have those two things being equal, which is good. That's what we expect to have happen if it's a midpoint, right? But main thing, take away from here, make sure you know your midpoint formula, make sure you know your distance formula and how to use it, right? That's what I'm trying to illustrate there. Okay. Moving forward, equations of circles, how do we work with those things? So determine the center and radius of a circle with the equation. So this looks nasty, right? You have x squared minus 4x plus y squared plus 6y minus 25. Okay, the main thing to remember is an equation for a circle looks like this: x minus h squared plus y minus k squared equals r squared. And you might be thinking, well, what the heck, that's a whole bunch of symbols. X and y are just your normal variables that you usually see. HK, so that is essentially an ordered pair, that's the center. So is the center of the circle? And then r represents the radius. R is the radius of the circle. So first things first, just to make our lives a little bit easier, you might think it's r squared, but it's not going to be right away. But let's start grouping some things in appropriate places. So with our equation here, we have x squared minus 4x plus, we have y squared plus 6y. And then move the 25 on over, because the constant should appear on the other side. We have all the variables here. What we want to do is turn this thing into an x minus something squared plus a y minus some number squared, right? Notice we don't have that because we have an x squared minus 4x. That extra x doesn't do it for us. So what we have to do is, it's called completing the square. And we'll have to complete the square for the x terms, and we'll have to complete the square for the y terms. So how do we do that? Well, if you recall, if you have a plus b, the quantity squared, that is a squared plus 2ab plus b squared. So notice, anytime we have some quantity squared, we're going to get twice the middle term being a product. So the way we do that, you see this 4 here, we can take half of that, right? We can write this as x squared minus, well, this would be 2 times 2x, but so that means that b in this case, well, so our a value is x essentially. I know I switched it around there, so you can write 2x 2 if you want, but essentially our a value is 2, so that means our b value has to be 2 as well. So, our a value is x and our b value has to be 2. So now notice what that gives us. Then we go plus b squared, so plus 2 squared. But I can't just toss in 2's willy-nilly. So if I add it in, I have to subtract it. And I just put it outside the parentheses. Parentheses aren't making a difference in this case. I'm just trying to do some grouping here. Okay, we got to do the same thing with the y. So notice if we go y squared plus 2 times, well, what's left over? Well, we have 3y, right? And then plus, we got to figure out what's our a, what's our b. Our a value, notice we started with y, so that's what's squared. So we have y as our a, and then b is 3. So in this case, we have 3 squared. And so then we can't just toss it in there. We got to subtract out a 3 squared. That way we aren't adding numbers that don't exist in the equation. So this thing equals 25. So now what we have, though, is we have a perfect square. So in our first case, we have, and notice I wrote plus b. I should be careful. Technically what happened here, let me put this as plus, and then this would be negative 2x in there. And then that means I can kind of get away with that. If I put a negative 2 in parentheses, notice it makes no difference when I square it. So I'm 2 squared, negative 2 squared, no difference whatsoever. So our first one was essentially x minus 2, the quantity squared, but then we have this minus 2, the quantity squared, that we'll have to deal with, plus the second piece is, what do we have here? We have y, and then it'll be plus 3, the quantity squared, but then we have to subtract off 3 squared, and all that equals 25. But notice this makes x minus 2, the quantity squared. So yeah, in your notes I see, so Josh posted something, said, in my notes I had completing the square as taking half of the leading coefficient and squaring it. So notice our leading coefficient in terms of the degree of the polynomial, in this case it's 1. And then in the other case it's 1, so we don't have to worry about that. But yeah, you're exactly right in terms of what happens, how do we complete the square in general. Yeah, I just took half of that term. That's what I was doing with factoring out the 2x, or the 2 out of each part. I'm trying to show you why it's half that term is kind of the idea there. So, but yeah, that's the same thing. Notice I just take half of 4, I get x minus 2, essentially, I'm good. If I take half of the 6 here, I get y plus 3, which is what I have here, and I'm good. You just have to remember to square that extra term, and I was just trying to illustrate where that's coming from. So if you know some formula, that's awesome. A lot of people tend to struggle with this stuff for some reason. So I'm trying to make sure we can brush it up. So notice when I add 2 squared over to the other side, I get plus 4, and then I add the 3 squared, that'll be plus 9. So this whole equation becomes x minus 2, the quantity squared, plus y plus 3, the quantity squared, and then that should equal, what is that, 29 plus 9, 38. Okay, so now this tells us something. This center is equal to, well, 2, and then notice we need y minus k, so this goes y minus a negative 3. So our center is at 2, negative 3. And then our last part's r squared, so technically this is the square root of 38 squared. So the radius, and the reason why we aren't using the negative is because we're talking distance when we're talking radius, so we only need positive values there. And so we have a radius equals square root of 38, and we're good to go. Okay, so that's one where we're working with completing the square and all that stuff, and to find the radius. On the other hand, you can do this other ways, right? So we can have equations of circles with endpoints of its diameter. So that means you have a circle. I'm not saying this is going to be to scale whatsoever, but I could have this be 1 point and this be 1 point, and then this happens to be the diameter of the circle. Well, notice I need to find that radius in that center. And so the way for me to find that radius in the center, first I need to find the midpoint, right? Because the midpoint would help us get there. So notice that makes, in this case, using that midpoint formula once again that we just saw on the previous page, you might recognize those numbers too. I chose very similar ones for a reason. So you have 10 plus 4 all over 2 in the second case. So notice that midpoint equals 1, 7. Okay? And now you can use your distance formula. Well, some of you might remember the distance formula from the previous page. So in this case, I'll choose the distance to be the radius. Otherwise, you could choose the distance between the 2 points listed right there, and also try and just take half of that to get the radius. That's another option as well. You're more than welcome to do that. But so notice if we go 7 minus 1, the quantity squared, plus 10 minus 7, the quantity squared, we get 36 plus 9. Remember, that was the square root of 45. And so just basically what we had on the previous page. So the equation for the circle, the midpoint happens to be your center, and then we have our radius down below. So this makes our equation being x minus 1, the quantity squared, plus y minus 7, the quantity squared, equals r, which is the square root of 45, squared. And so if you want a simplified format where you don't see the square root, x minus 1 the quantity squared plus y minus 7 the quantity squared equals 45. And notice that moves a lot faster if you know your midpoint formula, you know your distance formula. So I'd suggest once again writing those formulas down. Make sure now, in the big highlight in this one, is understand what the equation for this, given a center of a circle and a radius of a circle, trying to find that equation, or working backwards if you're given an equation, trying to build it into that format to work with a circle. So hopefully that makes sense. If not, let me know. I'm happy to address that question as well. So in terms of lines, the big equation there, you have a couple parts to it. The easiest equation I'd recommend, most people what they know, actually, I'll start with that one. Most people know this, y equals mx plus b. This is nice, it's hunky-dory, everything's fine, but I wouldn't recommend knowing that one right out the gate. The one I would recommend knowing is y equals m, y minus y1 equals m times the quantity x minus x1, where x1, y1 is a point on the graph, so all you need is 1 point, and m is the slope. And so in our case, our m, if we have x1, y1, and x2, y2, so you go x, oops, sorry, put the x's up there, y2 minus y1 over x2 minus x1. Another format you might see is the change in y over the change in x. That's what that stuff stands for. Another way you might see it is the rise over the run, right? And there's a whole slew of other ones. And you might be concerned about the order in which you choose your x1, y1 and your x2, y2. As long as you're consistent, notice the x1 and y1 appear on top and bottom of each other. Same thing with the x2, y2. It doesn't matter which one you choose, though, because if you reverse the order there, you're just getting negatives in both versions, and you're good to go. So if I multiply the top and bottom by -1, I get y1 minus y2 over x1 minus x2. Same equation, right? So I can put that into, whoops, I keep on wanting to put x for some reason. So this is the same thing as y1 minus y2 over x1 minus x2. Same song and dance. Okay, so let's get to our problem now. Find the equation of a line through the points. And then you have 7, 13, and -4, and 27. Okay, so hunky-dory there. First thing to do, though, so we need a couple parts. We need a point, so we already have that. And so now all we need is a slope, and we have our formula. And the reason why this is so nice, this is called the point-slope formula. So all you need is a slope and a point on the curve formula. Okay, so m in this case equals, we'll take, in this case we have our 2 points, so we'll go x1, y1, x2, y2. So we subtract the y's. I'll start with the 27. 27 minus 13, so that didn't matter which order we went in, but now it does. So we chose 27 first, that means we have to choose -4 first, because that's the associated x2 there. And then our other case is 7. So after all said and done, what do we get? We get 14 over -11. Okay, and we have a point. It doesn't matter which one we choose. So we go y minus, let's just choose our x1, y1. So y minus 13 equals, what do we have? -14 over 11. X minus x1 is 7 in that case. Okay, and remember, this is going to be the same as y minus 27 equals negative 14 over 11 x minus negative 4, or x plus 4. And the way to figure that out, you can just add the 13 over to the other side and then do the multiplication and find your constant. And you can put it in the first form, by the way, is called slope-intercept form. Okay, so you'd be good to go that way too. So another thing we can ask about intercepts, and we'll talk about intercepts a little bit more later. The y-intercept is where the graph of the curve crosses the y-axis. So that means when x equals 0, that's the big thing there. So same as song and dance, we can find the slope. So m equals, this one will look a little scarier. We'll go x1, y1, x2, y2. And so we get 12 minus 3 pi all over, what do we get, pi, or 6 minus pi. Okay, and it looks like it can factor nicely, but it can't factor much more because the pi's don't cancel because you have the minus terms up top. And even if you try to factor the top, you factor out a 3 and you're left with 4 minus pi, which doesn't cancel off with 6 minus pi. So that's your slope. It's not pretty, but it gets the job done. So now let's take our values. We go y minus our y1. Now you have choices here. You can use the pi's or the numbers. I suggest probably the numbers in this case. So y minus 12 equals m, which is 12 minus 3 pi over 6 minus pi. And then it goes x minus x1, which is 6. Okay, so now we're searching for the y-intercept. What do we need to do? Y-intercept. Pen's acting a little funky today here. That occurs when x equals 0. Okay, so we get y minus 12 equals 12 minus 3 pi over 6 minus pi times 0 minus 6. So you get y equals 12 minus 3 pi over 6 minus pi times negative 6, and then plus 12. So what does that become? Well, if we simplify this on out, we get the negative 6 on in there, so we get negative 72. Negative 6 times negative 3 pi is plus 18 pi all over 6 minus pi. And the second part, we need to make it 6 minus pi over that, so plus, if you put 6 minus pi on the bottom, you have to do 12 times 6 minus pi, which is 72 minus 12 pi. Okay, so notice your 72s will cancel, right? And you're left with 18 pi minus 12 pi, so notice that makes 6 pi. So our y-intercept occurs when y equals 6 pi over 6 minus pi. And you might be asked on a calculator to round so many decimal places. Just make sure you know how to do that. Yeah. So the question is, could you also use slope-intercept formula, plug in one of the x and y coordinates and solve for b? Yes, most definitely. Only reason I try and avoid doing that right away is it's just going to take you more time. It'll probably add on an extra, depending upon how proficient you are with the arithmetic here, but it's going to add on an extra few minutes. So rather than waste your time, I'd strongly suggest using that point slope formula as much as possible, unless it says put it in your slope-intercept form. And notice you'd have to do that here. So to kind of show you what's happening, what makes that a little bit hard. So go back to the previous problem. You get y equals m, which is 14, or negative 14 over 11, x plus b. So let's plug in a point, right? So I get, let's see, 13 is our y value. So 13 equals negative 14 over 11, and then times 7 plus RB. Now I have to simplify that on over, which this one's not as bad as the next one. I'm going to have to round most likely if I'm using a calculator, right? I have pi's involved with my formula. Notice I could handle this without using much of a calculator, right? None of this stuff I've used a calculator thus far. There will be a time coming up here when we get to the exponential equations that I'm going to use a calculator and show you how to use that. But all this stuff has been done without a calculator. If it does ask me to round, then I have to kind of work it out, and that's song and dance. But in order for me to do this, I can do all this stuff in my head, is kind of the trick. And so there's a lot of things you can do without having to bring out the calculator to have it do all the work for you. So, and that's what I'm trying to avoid. Just trust yourself, trust your instincts and stuff like that. Okay, so great question on that one. Evaluating functions, can we do that? Now, let f of x be this 7x minus 3 over 4 minus x. G of x equal 2 to the x, so we have an exponential function, and h of x equals x squared minus 7x plus 3. How do we find all these things? Well, f of 3, let's start with that. So f of 3 equals 7 times 3 minus 3 all over 4 minus 3. And so notice we have 21 minus 3, which is 18, I believe, and then this is over 1, so our answer is just 18. And all we did, and I'll draw the lines, so we had 3 replace x, so that means 3 has to go into that x, and 3 has to go into that x. That's all there is to it. That's all we did. Okay? Whatever goes inside, it must go into the next one. So in the g of negative 2, notice that we have, that's replaced this x, so it must replace that x as well. So we get 2 to the negative 2. Now this freaks out a lot of people. Don't let it freak you out. You see the negative exponent, all that does is that makes it 1 over 2 squared. So all the negative exponent did is just flip it so it's a fraction. Basically, you're looking at the reciprocal of that. So 2 squared is just 4, so you're left with 1/4. Okay. In the next one, people see this circle business and they freak out. Don't let it freak you out. All that is f of g of 3. Right? So notice first we have on the inside g of 3. So let's find g of 3. Notice that's meaning that we have to take this and that goes in for that x, so that must also go in for that x. So as a result we have f of, and then this becomes 2 to the third. Okay, but 2 to the third is just 8, so that's f of 8. Okay, so what's f of 8? Well, now we got to find the f function. Sorry for crossing lines there. I got to plug in for those two x's right there and there. So we have, this is 7 times 8 minus 3 all over 4 minus 8. So as a result, what do we get? We get 56 minus 3, which is 53. All that is over negative 4, and you're done there. Okay, so let's try this g composed with h of 2, see what happens. So that's g of h of 2, and I'll show you a different way to work it this time. So g of h of 2, so what we can do is this becomes, notice in this case we have h of 2, so here's a different route, and we'll get a similar answer. We could use it in the other case. You pick one what you like and you're going to be good to go. So we're plugging in h of 2 where we see an x, so I'm just putting 2 and then an h of 2 up there. Okay, but what's h of 2? Well, so notice h of 2, I have an x there, and an x there. So this becomes 2 to the, you get 2 squared minus 7 times 2 plus 3. Right? And so that makes, this is 2 raised to the, well, notice that makes 4 minus 14 plus 3, so that's going to be, whoops, that's a 3. Do not let your eyes fool you. So that's 2 to that's negative 10 plus 3 makes negative 7. And remember, we just talked about that flips this upside down, so you get 1 over 2 to the 7th. And you might be wondering, how do we do this in our head? Easy way to think about it, you probably know 2 squared and 2 cubed. 2 cubed is 8. So that means 2 cubed times 2 cubed is 8 times 8, which is 64. And so that leaves an extra factor of 2 times that. So 64 times 2 is 128. And so that's how you can kind of do that in your head. All I did is I broke this up into 2 cubed, and 2. So that's 8 times 2, so 64 times 2, and then that's just 128. Yeah, you can get the powers of 2 pretty quickly compared to some of the other numbers. So, any questions on that one? Please let me know if so. So I try to give you a couple different formats for doing that composition of functions. Make sure you understand what the composition of functions means, though. You're basically just putting parentheses and then plugging in the function into the other function. Okay? So, alright, and that kind of leads to this composition of functions is what's essentially happening when we're doing transformations. So what we're starting with in this case is a function f of x equals square root of x. So you get a function like that. So let's say y equals square root of x. Okay, and so we want to build to this g of x, but you got a whole bunch of steps. So let's call this step 1, we'll put a f1 of x. What do? We reflect f of x over the y-axis. So what does that do? Well, that should be, in that case, f of negative x. Because what it's done is it's reflected the domain. So now you have this graph that kind of goes this way. And so notice our x values should all be negative that we can plug in to give us a nice result there. So this is f of negative x. Okay, so that means that this becomes, well, what's f of negative x? Well, that would be the square root of negative x. So we have our new function now, f1 of x is the square root of negative x. And so in our next step, we're going to deal with f1 of x. So what's our next step? Step 2. Shift up 19 units. So we'll call this step, since it's step 2, f2 of x. So what we're going to do is we're going to take f1 of x, the way we shift up and down is add or subtract. So in this case it's up, so we're going to add 19 there. So this is f1 of x plus 19. So where do we go from here? Well, f1 of x we know is square root of negative x, so this thing is the square root of negative x, and then plus 19 is outside that root. Okay, so we have our second function, f2 of x equals the square root of negative x and then plus 19. So that should make our, so this was f1 of x. And what that did to our graph, we have 19 being the unit right here. And so you get something like that. So now, how do we move that? The next part. Well, we want to create our third step. And notice we're going to want to shift right. So this was F2. So this is 6, this is 19. We shift right 6 units. So shifting right's a little bit trickier. So what we're going to do is we're going to take f2 of x, and then we go x minus 6 on the inside. And the reason why, because notice you should be able to plug in 6 and get 0 inside of there, right? You get back to f2 of 0, okay? So, and that's essentially what's happened in this case. So we get, and most people trip it up, they think it's plus 6. That's the most common error that I see in this. So notice now, we have x right in here. That needs to be replaced with, because x was just right here, that's replaced now with x minus 6. So the whole quantity, x minus 6, has to be having this negative in here. Okay? Questions on that? Okay, and if you want to double check, always check the domain. So notice if I plug in 5 here, I get negative, and then I get 5 minus 6. 5 minus 6 is and I'll add the 19, don't let me forget that. 5 minus 6 is negative 1 on the inside, but when I apply a negative there, I get 1, which makes sense because I should get a value from the graph if you just take a look at it. So now what we have is this is f3 of x equals the square root of negative x minus 6 plus 19. So now where are we going from here? I'm going to change colors up. Oh, that was this one. Now we want to stretch graph vertically away from the x-axis by a factor 2. So we're going to take this graph now and we're going to stretch it away from the x-axis by a factor 2. So everything's kind of gone further away. Oops. Did I do that right? Sorry. I drew that a little bit too spot on there. Okay, so here is our old graph. So notice if we're stretching it away by a factor 2, I'm going to need to draw something else here. So when we're at 6, I know this won't look exactly right, but I'm saying the graph goes something like that. The new point that you'd have, instead of 19, you'd have 38, right? And that's what you're going off of. That would be, so this is f2 of x, or f3 of x. So our fourth one, we want to double it. So how do we do that? Well, you go and you double f3 of x. So yeah, great question. Can I repeat the step again when I shifted right 6 units? Yeah, good. Why is it in parentheses and all that stuff? So let's go back real quick before I go on to this 2 part. So when we're shifting right 6 units, one thing you might need to take note of shift left k units would be f of x plus k, and then shift right k units is f of x minus k. Those are the 2 main things that we have to focus on because it's a horizontal shift. So hopefully you recognize that this is horizontal in terms of a maneuver. So this is a horizontal shift. So it's left to right, and the horizontal, it happens on the inside of the graph. And if you want an example of that, let's take a look at x squared. So this is y equals x squared. Now I want you to look at what would y equals, so if I put the vertex here and I shift 1 unit to the right, what would that graph look like? And so notice our vertex is at 1, 0, right? So all we've done, if we shift that, we get y equals, now you have a choice, it's x minus 1 or x plus 1, the quantity squared. So let's try x minus 1, the quantity squared. When you plug in 1 here, notice you get 0. So, and that corresponds to that point. If I tried y equals x plus 1, the quantity squared, notice that would be occurring over on this side, right? Because when I plug in negative 1 is when I get 0. If I plug in 1, I actually get 4. So in that case, that would correspond to that vertex. And then I could draw the parabola that way. So when you're talking a shift right so many units, first off, you need to recognize that it's a minus inside the parentheses, just like we saw with the parabola here. Okay, hopefully that makes sense. Does that make sense so far, Charlotte? Please let me know whether it does or doesn't in terms of seeing why it's a minus, and then I'll kind of explain why it's the stuff's in parentheses. So when you're taking a look at this, why do we put it in parentheses in that formula? Well, notice our x minus 6 has replaced this x. So if we just had x and we put minus 6 outside of there, notice that becomes a vertical shift. So we need that minus 6 to be every single piece inside of here wherever we have an x, just like when we did the functions. So yeah, so in terms of oh, and the negative I see is another question. Yeah, so we have that negative. Why do we have to distribute through here? So if I chose just if I wrote it this way, square root of negative x minus 6, notice what happens to our domain. What's the domain of this? Oh, okay, good. So I see you're just answering. So if I go negative x minus 6, I need this to be greater than 0, right? And so you can add x to both sides. And so notice you get negative 6 is less than x. Or greater than x, I'm sorry. So negative 6 is greater than x. Notice when we drew our graph of what happened when we shifted 6 units to the right, that's this one, let me mark it right here. We wanted the domain to be from negative infinity to positive 6. That doesn't match our domain here. So we got a problem. Okay, so that's why we put that in parentheses. We want to try and make sure our domains match. And that's why I like drawing the graphs all the time too. Yeah, parentheses, yeah, so yeah, like we put it in parentheses. Yeah, it's exactly right. So hopefully that makes a little bit more sense in terms of why it's in parentheses, why we're shifting left with this parentheses there. What I always go back to, let's say you're struggling on an exam, you don't remember, go back to the x squared graphs. Those ones are a little bit nicer. The only time you can't really use those is when you're reflecting over the y-axis, because it's symmetric over the y-axis. So, but those are the easier ones to do, and you can graph them real quick. So I'd highly recommend using those as your kind of go-to examples. So hopefully we're all back in good shape here. I'm glad questions are being asked. That's exactly what I want to see. So now we have 2 times f of 3 of x. This is what trips people up a lot of times. So it's 2 times this whole function. So this is 2 times f of 3 of x, f sub 3 of x I should say, is square root of negative x minus 6 and then plus 19, right? And all that is multiplied by. And you can check it because notice we said we went from 619 to 638 just by doubling it because we're stretching by a factor 2 away from there. So if you plug in, let's plug in 6, see what happens. You get 0 underneath the square root. You get 19 times 2, which is 38. That's matching up. Everything's looking good, right? So that means f of 4 of x, f sub 4 of x, I should say, equals 2 times, and you can multiply that 2 on through if you want, or you can just leave it as is. I just leave it as is for simplicity's sake. And then if you need to brush it up, say it's a multiple choice question, you just do that when necessary. So the last piece is to take this whole thing and reflect it over the x-axis now. So this would be 6, and then that means this coordinate would be negative 38. And you notice, so I'm just drawing this stuff. I'm not as concerned that, do I need every point drawn out? No, I just want to get the locations of certain points that help indicate what's happening to this graph. Granted, I should be a little bit closer when I did the stretch by a factor of 2, but at the end of the day, I still get at that answer. So now this final one, though, what's so important is it's g of x. And how do we reflect the graph over the x-axis? Well, you take the previous graph and you just put a negative on the outside, so negative f4 of x. So this thing becomes negative, and then you have the 2, and so I'll put it in parentheses. You don't need it because you can distribute it and all that jazz, but just so you can get the gist of what happens in general. Negative, and then we have the quantity 2 times x minus 6, or 2 times the square root of negative the quantity in parentheses x minus 6, and then plus 19. And so if we wanted, if someone said, oh, you got to brush this up, and okay, whatever, we can do that too. And the way we do that is negative 2 square root of negative x. Well, actually, let's brush this up a little bit more. So we can make this negative x plus 6. And then negative 2 times 19 makes negative 38. And then you can see it matches that value there. Okay. So that's all we're doing. The biggest trick to these are, I recommend drawing the graph along the way to kind of see your steps. And you see how I do the sequence of steps rather than try and just guess it all at one moment in time. So that can help you a lot of the times too. So keep that in mind. If there's any more questions, let me know. I'm glad to help on this. I know there were some struggles on transformations. I have other videos associated with it too, but I'm happy to help out some more if you're struggling with it. So just let me know. Alright, so the next bit, I'm going to actually elaborate a bit more than just draw the graph. So in terms of draw the graph, you could get some key components just by kind of looking and seeing what's happening. So right now I can tell you it's going to be a parabola because the degree of the polynomial is a square. Yeah, it could. So the question is on this, could you check your work by plugging it into a calculator? Yeah, most definitely. On this, I would strongly suggest it if you have the calculator there. Everything I'm doing thus far, though, just so you know, I don't have a calculator nearby. I actually do have one. I'll use it in a little bit. You can see the thing right here popping up. So that is going to be, we'll use the calculator soon enough. But for right now, don't need it. It's okay. We can work without it. So, I don't want to close that. Didn't mean to do that. Okay, let's bring that back up. Sorry about that. Got a little excited there. Alright, back to the draw on the graph. So this thing right here, the best thing to do is complete the square as best as possible. And you can draw this graph without a calculator, and that's kind of the point I'm trying to get at. And gather a lot of information. So the first thing, though, what I do is I factor out a 2 out of the first two terms. So you can write this as 2 times the quantity x squared minus 2x. And then plus the 5 we'll just leave out there. And why would we do such a thing? Well, now with this we can complete the square of that inner term. And so what we get is f of x equals 2 times, now if you struggle with completing the square, let me know. So x minus 1 squared, notice that gives me x squared minus 2x, but then it adds 1, so I have to subtract 1 here, and then I have to plus 5 this thing. Okay? So at the end of the day, what do we get? Well, we get f equals 2 times the quantity x minus 1 squared minus 2 plus 5. F of x equals, this is 2 times the quantity x minus 1 squared, and then plus 3. So big things, some big takeaways I should say right away. This tells us about the vertex of the graph. So you have the vertex of the graph. And so this thing occurs at, in our case it'll be 1, 3. And how do I get that information? Well, this tells us is that we shift right 1 unit. And this tells us we shift up 3 units. Right? Ah, yes, so that's exactly right, right. So I'm going to explain in a second. Kate made a great point. She said, hey, isn't it just negative b over 2a? Yeah, that's the x-coordinate. You could use that right away. So you go negative b over 2a, that'll do the trick for you every time. Now, where does that come from is the real question. That's just the x-coordinate though, and then you got to get the y-coordinate. And I can give you the whole formula and how that works out real quick. The main thing though, so we get that vertex, now we're good to go. And so we know we start at 1, 3. So we'll go 1, 1, 2, 3. And so when you plug in, by the way, you can start plugging in some numbers. But if you plug in when you get 0, and you should know, rather than being up 1 unit on either direction, it's going to go up 2 now because we have that vertical stretch away. And so our whole graph, in a matter of a few seconds, sorry for my pen kind of sliding there, but you can get your graph really quick. And so, yeah, and exactly, so the vertex is you get negative b over 2a and f of negative b over 2a. I can give you a general example of what happens. If you did ax squared plus bx plus c, my claim, and so what Kate's kind of mentioned off on the side in terms of how to find that vertex,
It's exactly right. You can rewrite this. This is a times x plus b over 2a, the quantity squared, plus c minus b squared over 4a. Okay, you might be saying, well, who the heck cares about that? And I'll show you why. This gives us the vertex right away. So the vertex, well, first off, I'll show you that this works. Notice this thing would become a, and this is x squared plus 2 times b over 2a x, and then plus b over 2a, the quantity squared, and then plus c minus b squared over 4a. If you multiply this on out, you get ax squared. Notice your 2's cancel just by completing that square, so you have bx, and then the a's would cancel when you multiply that out. So you get ax squared plus bx plus, in the next term you have b squared over, it would be 4a squared, but then one of those a's would cancel off with the a being multiplied outside the parentheses, so you have b squared over 4a plus c minus b squared over 4a. So notice those things cancel. So you have the same original equation. You might say, okay, whoopity-doo, what did you just do? Well, actually, I gave you the vertex every single time. So this is your y-coordinate, and this is telling your x-coordinate. So anytime you have ax squared plus bx plus c, your vertex occurs at negative b over 2a, and your y-coordinate would be c minus b squared all over 4a. And you might not believe me, and that's good. You should be hesitant to believe me with a lot of this stuff. So just to kind of prove the point, though, I'll try and do this. You have a equals 2, b equals, don't let your eyes fool you, that's a negative 4 sitting right there, and c equals 5. Okay, so negative b over 2a, let's start with that. So that would be negative, and b is negative 4 over 2, and then a is 2, right? So then our other one, c, which is 5, minus b squared, so that would be negative 4 the quantity squared, all over 4a. So that'd be 4 times 2. So what does that become? Well, the first one, negative negative, makes a positive, so you have 4 over 4, which is 1. Okay, so our next one, we have, well, let's figure out what this is. This is 16 up top, and this is 8 down below, so that's 2. 5 minus 2 gives you 3. Notice this happens to match that right there. And so you have your general formula to find the vertex every single time, if need be. So yeah, that's exactly what you want to try and be able to look for, is get that vertex, make it your life nice and simple. So its formula is negative b over 2a, and then c minus b squared over 4a. It works every time. So, and how do we actually come up with this formula right here? Just completing the square. That's all that was done. So just complete the square, and you're good to go. That's where that came from. If you want to see that, I'm happy to show you that too. So just let me know. But yeah, very good on knowing that formula. So now moving forward, average rate of change. What the heck is that all about? So average rate of change, say you have a function. I'm not saying this is the function that we're talking about here. So if you have some function going all over the place, and let's say we take a point A and we take a point B. So this is A, this is B. All average rate of changes looking for, and this is a formula you're going to want to know. So average rate of change. If this is some f of x, well, all average rate of change wants is the slope of that line that I just drew. Okay, so that means if that's f of x, that means that has to be f of a, and that means that has to be f of b. So this is b f of b, and this point is a f of a. Okay, so our formula goes f of b minus f of a all over b minus a. Now, could I switch it around? Could I go f of a minus f of b all over a minus b? Yeah, you can do that too. As long as you don't switch the order of, like, I can't do f of a minus f of b all over b minus a. That's the only thing. I can't switch one of them and not the other. So, as long as I do that, I'm good to go. So in our case, our interval is 1, 3. So the first thing you're probably going to want is f of 3 and f of 1. So f of 3 is just 3 cubed minus 3 times 3 squared plus 2 times 3 minus 5. Oh, 2 times 3, not 2 to the third. Sorry about that. Okay, 3 cubed is 27 minus 3 times 3 squared, that's 27. They cancel. So plus 6 minus 5, that thing should equal 1. F of 1, we get 1 cubed minus 3 times 1 squared plus 2 times 1 minus 5. So what does that equal? So that's 1 minus 3, which is negative 2, plus 2 is 0, and then so minus 5 sitting right there. Now, we just find our average rate of change. I'll abbreviate that AROC if y'all don't have any problems with that. So our average rate of change equals, it should be f of, I'll use 3 first, and so that means I have to use 3 down below first. So what do we get? F of 3 is 1 minus, and then f of 1 is negative 5 all over 3 minus 1, so that makes it 6 over 2. And so our answer would equal 3. And that was our final answer. Okay, big thing, what you want to take away, average rate of change formula. F of b minus f of a all over b minus a, whatever your interval is. And so just make sure you can, notice I'm giving you formula after formula after formula. As long as you know the formulas and how to apply them, you're going to be in great shape. So that's what we're kind of looking for. Trying to be able to apply the stuff you learned in here. So, moving forward. Determine the domain and range of the following function. So the domain on this one's pretty easy. Notice I can plug in any value for the x. There's no worry about that. So our domain is negative infinity to positive infinity. You can plug in all real numbers. There's no violation. I can square every number. I can multiply every number by 6, so or negative 6. Doesn't make a difference. So our domain is that range. Now, the range is going to be a little bit trickier, and that's where you want to find the vertex. You could use a negative b over 2a and all that jazz, or you can complete the square. I'll go back to completing the square just because it tends to give people a little bit more trouble. So x minus 3 at the quantity squared, but notice I added in an extra 9, so that means I got to subtract 9, then I go plus 8. So that means that this equation is x minus 3 the quantity squared minus 1. Alright, so from looks on the graph, what we've done is we go 3, we go minus 1, and that's our vertex, and then we can kind of go from there. Right, now notice I'm getting kind of lazy in how I draw it. I knew it was upward facing because I see no negative symbols out in front of the square. Yeah. So if we keep on going, oh, so yeah, I know the formulas, good, because the homework was more complicated. Yeah, the homework can seem complicated at times, but basically it's looking for applications of formulas, making sure you can do those inside out, up and down. That's what we're kind of looking for here. So in terms of what we have on this problem, what's our range? Well, if you look at the graph, notice it can't go below negative 1, but it does reach negative 1. So our range, we start at negative 1. And we want to include it, so we'll put that, and then we want to go all the way up to positive infinity, and that's what we get right there. Okay, so now moving forward, how do we figure out domain for the following functions? So for g of x, the only time we have to worry is when the denominator equals 0. So x squared minus 8x plus 15 cannot equal 0. So that means what we actually do to solve it, we set it equal to 0. X squared minus 8x plus 15 equals 0, which is the same thing as, notice this one can be factored. So this can be factored to x minus 5 and x minus 3. Okay? Okay, good question. Going back. Why is negative 3 squared not positive 9? So I moved a little faster there, so I'm glad you slowed me down. Completing the square. So notice if I go x squared minus 2 times, or let me do plus 2 times negative 3x, and then notice that would become plus negative 3 squared, right? But when I squared that, I just added in a 9, so I have to subtract a 9 on the outside, and then plus 8. And so what you saw is I gave you an abbreviated version, that x minus 3, the quantity squared, that's all this junk right here. Okay? So you had a plus 9 sitting inside, so you had to subtract off the 9 to make that go back down to 0. Basically, I need these two parts, this and this, to cancel. Right? Otherwise, I've changed the equation. I got a new equation. And so that's what we're looking for in terms of we want those things to cancel. So that's why we put the minus 9 in there. Okay? Does that make sense on that part? Just let me know if not. Okay, good. Great job asking questions, folks. Yeah, that's exactly what I'm looking for. So any questions you have, that's what I'm here for. So notice back to our domain problem, we have x equals 5 and 3 would be the problem. So that means, and so this is kind of the side note, right? So we get x cannot equal 3 nor 5. And so what you see sometimes is people want this in interval notation. So the way to fix that, you go from negative infinity to the smaller of the two numbers, so you go 3, and then you have a union. You don't want to include them once again, so you have parentheses. You go 3 to 5, and then you have another union. And then you go from 5 to infinity. If you struggle with that, let me know. We can draw a number line. That helps a lot. Just draw on the number line, put the open circles, and then you can go from there. But speaking of number lines, that's what I'll kind of do on this one. In this case, what do we need? We need the square root to be greater than or equal to 0. So this thing becomes, we can factor this. So this is x. We can go minus 6 and plus 4, I believe. And so the way we solve an inequality where we have a quadratic, we can create a number line. And we can put in the values where this thing's going to equal 0. And just so you can see where they equal 0. X minus 6, x plus 4 equals 0. You set each factor equal to 0. You get x equals 6 from the first one, and then you get negative 4 from the second one. So that means we have negative 4 and 6 somewhere on here. And then what's happened, I'm putting a solid dot here for now, because h of x will equal 0 right when those two occur. Now what we have to figure out is it positive or negative? Because if it's negative on this certain interval, then we've got a problem. And notice it can't be 0 anywhere else except for those two places. So that's the beautiful thing in terms of what we have. Now this breaks us up into 3 different intervals, just like you saw before. So we have from negative infinity to negative 4. Remember, there can't be any 0, so either it's always positive or always negative. And negative 4 to 6, there's no 0, so it's always positive or always negative. And same thing with 6 to infinity. So if we're taking a look at this, negative infinity to negative 4, plug in a number. Let's plug in negative 5. So you go negative 5 here, negative 5 here. Notice we get a negative overall in this part, and we get a negative overall in this part. If I multiply two negatives together, I get a positive. And so that makes this positive on that interval. Okay? So that means, since it's positive, that is greater than or equal to 0 there. So we're shading this interval in. So that's going to be a part of our domain. Okay? Now let's pick something in between negative 4 and 6. And I'll erase that negative 5 down there to plug it into our equation here in a second. And you can plug it into your original. That works just as well. Let's plug in 0. So notice when we plug in 0, we get a negative here and a positive here. A negative times a positive is a negative. That does not satisfy our equation, so we are not going to shade it in this case. Okay, so now we'll move on to 6 to infinity. So what is that going to look like? We'll pick a number, let's say 10. So if I plug in 10 here and 10 here, notice we get a positive in the first case, a positive in the second case. Positive times a positive makes a positive overall. And that means we are going to shade this in because it satisfies our inequality. So at the end of the day, our domain, in this case, we have negative infinity, but notice we now want to include negative 4. So negative infinity all the way to negative 4 and include it, so we'll put a bracket. Same thing here, we want to include 6, and then we want to take that to infinity. And that's how you do your domains. All right? We can work with radicals, we can work with rational functions, doesn't matter, we know how to handle those things. Okay, so find all asymptotes and intercepts of the following functions. So let's see something that's a little bit more interesting in terms of that. So we can work with asymptotes or intercepts first. I'll just, if you want it on the first problem, I'll actually let you decide. What do you want to work with first, asymptotes or intercepts? Which would you prefer? Yep, I figured asymptotes. So asymptotes it is, and then intercepts I'll do over on the other side there. So there's two types of asymptotes. One is going to be the vertical asymptotes, and the other is going to be the horizontal. I would say the horizontal are the easier of the two, so let's get them out of the way. Okay, how do we check for horizontal asymptotes? Just check the degrees of the polynomial. Okay, they're the same in this case. Since they are the same, you just look at their leading coefficient, so you see those two coefficients right there. So horizontal asymptote at, it's always a y value, it's not an x for horizontal. Remember, horizontal is dealing with y. So horizontal asymptote at y equals just those leading coefficients, 3/2 done. That's it. If the degree of the numerator is larger than the degree of the denominator, you have no horizontal asymptotes. If the degree of the denominator is larger than the degree of the numerator, then you have a horizontal asymptote at y equals 0. Those are the three scenarios, that's it. Okay, so this one was pretty nice there. Now for the vertical asymptotes, we're going to need to factor things a little bit nicer. So we have 3 you can factor out of the top, so you get x squared minus 3x, and then what is that, minus 10. And then down below we have 2, and then we have x squared minus 8x plus 15. So notice in our numerator we have 3, then we have x minus, what is that, 5, and then x plus 2, I believe. And down below that would be 2, and then we have x minus 3 and x minus 5 are the two numbers that multiply to give you 15 and add to negative 8. Okay, so this tells you some information. Notice you have an x minus 5 here and an x minus 5 there. That means we have a hole because the multiplicities are the same. So the hole is at x equals 5. Yeah, that's exactly right. Removable discontinuity. So that's the tricky part. Most people just set the denominator equals 0, don't worry about the numerator. You got to worry about the numerator just a little bit. So you're just trying to double check. You could always just solve for the denominator and then plug that number into the numerator, see if it's 0, and if it's 0 then you got a problem that you got to double check on. But if not, then like in the case, notice what we have is we do have this case when x minus 3 equals 0. That is going to be an asymptote because there's nothing to worry about in the top. So this means that we have a vertical asymptote as at x equals 3. So bada boom, bada bing, we're done there. Okay. So now we've taken care of the asymptotes in this case. Let's take a look at, and so I'll put that hole over here. So hole at x equals 5. You can even find the y value, by the way, if you ever were interested. So you can plug it in into the other pieces. So notice we get 3 times 7 is 21 over 4. That's actually where the hole would occur if you were to draw the graph. But that's not a major importance in terms of finding that y value, but just neat little factoid, I guess you could take. So intercepts, what's going on here? Okay, so we have two things. I'd say the easiest of all is the y-intercept. And why is that? Why is the y-intercept so easy? Well, that has to be every time. That's going to correspond to g of 0. Or if it's an f function, it's f of 0 or whatever the case may be. Well, notice if you plug in zeros, all you're left with, you get, I'll write it out, 3 times 0 squared minus 9 times 0 minus 30 over 2 times 0 squared minus 16 times 0 plus 30. All you look at is the constants. Yeah, that's exactly right. So x equals 0, that's all you're looking for. So this thing equals, and every time, I didn't even have to really plug it in. I just look at the constant terms and I get the values. So the y-intercept occurs, if I want to write it out this format, I can do it this way, 0, negative 1. Okay? So the x-intercept, that occurs when the numerator is equal to 0, as long as it's in the domain. Okay? Well, notice we already have this thing factored. So you have a whole at x equals 5. That would have been when the numerator equals 0, but since you have this factor here and this factor here, you got a problem. It can't be an x-intercept. Okay? So that means what we're left with is just this term right there. The 3 isn't going to play a factor. So it just occurs when x plus 2 equals 0. Well, when does that equal 0? When x equals negative 2. And so that means our point is negative 2 comma 0. And you're done. Okay, so that's that problem. Let's raise the stakes a little bit more, see something a little bit different. So let's look at h of x here. X squared minus 6x plus 8. So first off, this can be factored. Let's factor it. And then we'll talk about, and you all can write down in the meantime, what do you want to solve first? Do you want to solve asymptotes or intercepts? You just let me know. But in terms of the factoring, each of these can be factored nicely. So we have x minus 2, x minus 4 for the numerator. In the denominator, you might, some people remember it quite well, some people don't. Difference of cubes, because this is 5 cubed. So that goes x minus 5 in that first bit. And then it goes x squared plus 5x plus 25 in that second part. So if you have a preference in terms of asymptotes or intercepts, let me know from there. But notice we have no factors in common, so something interesting is going to happen in that case. So I don't see anything happening right now, so I'll start with that asymptotes again, just because it worked out so well last time. Are there any horizontal asymptotes in this case? So first off, do you think there's any horizontal asymptotes? And if so, let me know where they occur. Good. Kate, you can send me an email. That was perfect. So Kate said y equals 0. It's right on the money. Send me an email. I'll get you a bonus point coming up on that most recent quiz. So in this case, how was she able to tell where the horizontal asymptote occurred? So if you notice, the degree of the denominator is larger than the degree of the numerator. So what happens is, that means that since the 3 is greater than 2, you have a horizontal asymptote at y equals 0. Okay? You're only going to have, in these rational functions, you should only have, as long as there's no like square roots or anything involved, you're going to have just one horizontal asymptote. Yeah, and that's exactly right. Degree of the denominator is greater than the degree of the numerator, so that tells you you have a horizontal asymptote at y equals 0. Now the vertical asymptote's a little bit harder, right? There's going to be one that's easy, x minus 5 equals 0. But then you have another one, x squared plus 5x plus 25 equals 0. Most people will say, oh, that's just x plus 5, the quantity squared, and it's not really, because that would be a 10x in the middle rather than a 5x. So in the first case, you get x equals 5. That's going to be a problem point, so that's going to be a vertical asymptote. Now, we got to check and see, can this part be equal to 0? And so we need our quadratic formula in that case. So it goes negative b, so negative 5 plus or minus the square root of 5 squared minus 4 times 1 times 25 all over 2 times 1. But notice that this would produce an imaginary, because 25 minus 100 is negative 75. So that means there's no solution in this case. And since there's no solution, you're done. So hopefully, did the factoring make sense, and did the that piece of why there's no root to that part? Yeah, so Charlotte's asking a great question. Does the vertical asymptote focus on the denominator? Yes, that should be your main focal point, but the first problem I wrote, I wanted to try and show you, you can't just look at that alone, because notice when we had in the first problem, I had an x minus 5 here and an x minus 5 up top. That meant that there's actually a, you have a hole rather than a vertical asymptote. And the reason why, first off, the multiplicities of that root, x equals 5, in the denominator, it is the same multiplicity. It does get different if you have differing multiplicities. There would be a chance for a vertical asymptote. But since they're the same multiplicity, it becomes a whole. So I can't just say, oh, set the denominator equal to 0. Okay. So now, I saw, wait, can you show that again? So back to this, how we solved it. What we used is a quadratic formula. And so let me explain that real quick. You have ax squared plus bx plus c equals 0. And so you're going to love my singing voice. It's the best one I'm sure you've ever heard. It goes negative b plus or minus square root b squared minus 4ac all over 2a. And so that's your quadratic formula, in case you don't remember it. So now that we have that, all I did was just plug in the numbers. So your a equals, and you don't see a right there, but a equals 1. Your b equals 5. And your c equals 25, right? And so we're just plugging into that formula. That's where the negative 5 came from. So negative 5, notice that will correspond to this part over here. So negative 5, and that's our b value. And then we have our b value being squared. That's what's happened right here. Okay, then we have 4 times a, so 4a, and then c. And so notice that that became square root of, let me focus on that, that's 25 minus 100. And so that became the square root of negative 75. We can't take a square root of a negative number unless we're dealing in the imaginary numbers. So since we aren't, because we're drawing graphs, and graphs are real numbers in the x-coordinate, real numbers in the y-coordinate, what we have is this imaginary, so there's no solution to that polynomial in the real numbers. Meaning that x equals 5 is our only vertical asymptote. So that's the reason why we get away with saying that. As soon as we saw, that's called a discriminant. When we looked at that discriminant and it was negative, we knew right away that this wouldn't work out. Okay. Hopefully, does that make sense on that part? And to answer your first question, does the vertical asymptote focus on the denominator? Yes, that's the focal point, but just because you have a 0 in the denominator, that does not mean necessarily that it's a vertical asymptote. You also have to check the numerator, make sure it's not a 0 in the numerator. Okay, so but if you have, like in this case, 5 was a 0 in the denominator, not a 0 in the numerator, so we knew right away had to be a vertical asymptote. Okay, so with that, I'm going to try and create some space to try and fix that. And so yeah, if there's any more questions, please let me know, and hopefully that cleared it up. If not, Charlotte, please let me know. That's what I'm here for, just to try and help out as best I can. Okay, awesome. So we have intercepts left, right? And so we have that bit. I'll try and fill this in with this last piece. So our y-intercepts, remember, that is just plugging in 0 in for the x. And remember, I also gave you a shortcut. You plug in 0 for the x's, all the x terms disappear and you're left with just constants. So it's 8 over negative 125, and you're done. So your y-intercept is 0, negative 8 over 125. Okay. If you want to see me plug that in, let me know. I'm happy to go back and do that. Now for the x-intercepts. Notice there were no factors in the numerator that appear in the denominator. So all we need to do is set each factor, since we have things factored up top, equal to 0. So we go x minus 2 equals 0 and x minus 4 equals 0. So notice we get x equals 2 and x equals 4 for those x-intercepts. So this is x equals 2 and 4. If you want to write them as points, you get 2, 0 and 4, 0, and you're done. So hopefully that makes sense on that part. If not, let me know. But those are y-intercepts, x-intercepts. Notice the best thing for us to do is factor. If we factored, good to go. Alright, so now we're getting to the fun stuff. Find inverses of the one-to-one functions. Okay? So there's a step-by-step process to doing this. And how can we go about doing such a thing? Well, the step 1. So you'll see my first step here. Replace f of x with y. So in our first case, y equals 3x minus 8 over 4 minus 5x. Brings us to step 2. And so step 2 is solve for x. Sounds simple, that's the hardest part. That's the whole gist of this. So in this, what makes it hard is because we got a fraction. So the way to get rid of the fraction, you multiply both sides by what's in the denominator, and that'll cancel what's on the right hand side, and you're left with 4 minus 5x equals 3x minus 8. And we want to solve for x, so in order for us to do that, we're going to need to distribute on that left hand side. So you get 4y minus 5xy equals 3x minus 8. And the way we ever solve for a variable, we always get everything involved, especially these are linear for this. So it's x to the first power here, x to the first power there. Get all the x terms on one side and everything that's not an x on the other. So that means we'll add the 8 to both sides. So you get 4y plus 8 equals 3x plus 5xy. Okay, so now what do we do? This is where it gets a little bit trickier. Notice you have x terms on both of those terms on the right hand side, so we'll factor out an x. So you get x, and then you get 3 plus 5y, and you have 4y plus 8. And so now we could divide both sides by what's on the right hand side, multiply back, so 3 plus 5y should appear in the denominator. And so that leads us to step 3, now that we solve for x. Okay. Oh, okay, sure. So the question was, can I show getting rid of that fraction? Sure. I'm happy to do that. So all I did was I went y times 4 minus 5x equals 3x minus 8, 4 minus 5x times 4 minus 5x. And if you aren't sure about that, pretend I had a 3 in the denominator. Say I had 7/3 and I had x here, right? And for some reason, let's say I wanted to write another equation. So I wanted to write 3, I multiply on both sides. Well, notice what happens. I'm left with 3x equals 7. So same thing happens here. I get 4 minus 5x is cancel, and I'm left with, well, I wrote it on the other side, sorry. 4 minus 5x times y is the same as y times the quantity 4 minus 5x. So, but that's all that we were doing is, if x equals 7/3, that's the same thing as saying 3x equals 7, right? That's all there is to it. So yeah, that's what we're kind of getting at in that song and dance. Does that make sense on that, or did I lose you? Just let me know in terms of what's happening there. But yeah, that's every time you have a fraction and there's a denominator, and that's the only thing you have to worry about. Just multiply by the denominator on both sides, and the denominator on the one side will cancel if that's your only denominator appearing. So it's a neat little trick that can be used over and over and over again. So in our last step, what we do is we replace x with f inverse of x, if it's f is our function. And after that, we replace y with x. And so in our case, we have f inverse of x equals, so we replace that, now we replace the y with x, so 4x plus 8 all over 3 plus 5x. And you're done. And that's all there is to it. So we could do the same thing in the next problem. Only thing is, instead of f of x, we have a g of x. So we're going to, instead of replace f of x with y, we replace g of x with y. So how do we get rid of a cube root? What do we do to both sides? Well, we cube it. So you get y cubed equals the cube root. I'll actually show that extra step. Hopefully that'll help this time around. So we get that cubed. So that means y cubed equals 7x plus 11. We're solving for x, so y cubed minus 11 equals 7x. And divide both sides by 7, so you get x equals y cubed minus 11 divided by 7. And so now we're ready to do that last step. Replace, instead of f inverse of x, we're going to get g inverse of x. And now we have x cubed minus 11 over 7. And that's our final answer. Okay, so hopefully that makes sense in terms of what's happened for that problem. So if not, let me know. I'm happy to clear the air on that one. Oh yeah, so now we're on logarithms. Okay, good stuff. So there's a couple ways to do these problems. Method 1 is to understand what it means to have log base b of x equals y. Well, what that means is b to the y equals x every time. Okay? So in terms of this problem, what you see here, you have log base 3 of 81. So what I'll do is I'll rewrite this as log base 3 of 81 equals y. And notice that makes 3 to the y equal to 81, according to that formula that we just wrote up over on that side. So 3 to what power gives you 81? So notice if I square 3, I get 9. Oh, and then 9 squared would give us 81. But so I need to square 3 squared. That means I have 3 to the 4th equals 81. And you can double check that if you don't believe me. So log base 3 of 81 equals 4. And that's our final answer. So in our next one, there's a couple ways to do this as well. One is to use, how familiar are you with the law of logarithms? So that's what I want to know. If you're familiar with the law of logarithms, you can make this really easy if you know your properties. So I could kind of show you log base b of x over y equals log base b of x minus log base b of y. Okay, that's one route. Other things you can notice is if you have a log base b of, these are some properties that you might want to know. Log base b of 1, that always will equal 0, since, and let me explain that a little bit more, because b to the 0, I don't care what b is, it will always equal 1. And then you have log base b, if you have b to the x, well, that should always equal And the reason why these are kind of inverses of each other, but notice if I raise this over to this power, I get b to the x equals b to the x, and so they match up, right? That's what we're looking at. So why would I say that stuff? Well, all that silliness becomes log base 5 of 1 minus log base 5 of 5, or 5 to the first, which might be a little bit easier. And notice that becomes 0 minus, using that second property, these things match up. So I get 0 minus 1, and so that equals negative 1. And so notice that didn't take too long for us to do. Another way you could have seen it, though, using the first formula, I could have written this as log base 5 of 1/5 equals y. And so that means 5 to the y equals 1 over 5. But remember, 5 to the y equals 5. So 1/5 is 5 to the negative 1. And that's technically what I could have done in the first case. 81 is just 3 to the 4th. And then I have y equals 4. So in this case, you get y equals 1, or negative 1, from that route. There's tons of different ways, and I'm actually going to try and show you a few more coming up. So now on the next one, let's see how we could solve this. So if we set this thing equal to y, notice we have 8 to the y equals 2. How in the heck do we go about this thing? Right? Because we have a number larger than 2, and if I make it a negative exponent, it turns it into the denominator. So I'd have like 1 over 8 to some power. So it's got to be something that's not negative and something that's not greater than 1, so it has to be between 0 and 1. But an easier way for us to take an approach here, 8 is just 2 cubed, right? And this is 2 to the first. So that means we have 2 to the 3y equals 2 to the first. Ah, yeah, so I see it change 8 to 2 cubed. That's good. So what does that mean? Well, we get 3y equals 1 and y equals 1/3. And if you think about that, I'll just kind of explain what happened. The 1/3 power is a cube root. The cube root of 8 equals 2, and that's what's happened there. So log base 8 of 2 equals 1/3. Now, all these are good formulas to know. And I'm going to toss in one more. It's called a change of base formula. And why is that? Well, you could start this one and try and figure out, what is this? Well, this is 7 to the y equals 323. Well, I don't know what this thing is, because if you notice 7 squared, that's going to equal 49, right? And if I take 7 cubed, what should that be? Well, that'd be 280 plus another 63. That'd be 343, right? Uh-oh. So that means this number isn't going to be something nice. It's some number in between. Notice our exponents here were 2 and 3, but we don't know yet. And so if we wanted to get an exact answer, we need to do some work. And so what this change of base formula says, if I have a log base b of x, there's common logarithms on your calculator. And what you could do is you could convert this thing into this ln. What does that stand for? Ln of x, by the way, is log base e of x. And what is e? Well, it's just some fancy number, 2.71828, so on and so forth. Right? So it's just a special base. The other one that you can use is a logarithm, a regular log. So log of x without the base sitting there, that's technically standing for a log base 10 of x. You could use that. Both of those are on your calculator. So what happens is, though, you could change this formula from the log base b of x to the natural log of x divided by the natural log of b. And what that'll allow us to do, and so I'll put a question mark there, so instead what we'll do is we'll write log base 7 of 323 as equal to the natural log of x divided by the natural log of b. Oh, I'm sorry. So what's x and what's b is kind of the key question. Well, x is now 323, and your b is now 7. Yeah, so I see a question. Can you do a problem with something similar to finding the difference of logs? Yeah, I'm actually going to do a problem coming up where we're going to use the quotients and kind of work those as well. If it's coming up, well, here I'll show you real quick. Then the very next page, do you see that problem right there? So if you take a look, and if that problem doesn't look like something you're looking for, notice I have a log base 3 of x plus 7 minus the log base 3 of x minus 4 equals 2. That's what we're solving next. So you're one step ahead of me. If that doesn't work, if you're looking for something slightly different, just kind of explain a little bit more what you're looking for and I'll kind of help out. But I try to hit along the lines of all those problems. The main thing though is on this change of base, you could use this or you could use the log of x over the log of b. Big thing to take note of. Notice the x is what's inside the parentheses initially and the b is what goes down below. So notice we said before this should be a number between 2 and 3. Let's see if we can make it such a thing. So your natural log button, you have an E button, right? Remember when I said E was that 2.71828? So just in case you didn't believe me, here's the E button. So second E, and I said, hey, this is going to be some 2 point something something something. What do you know? 2.718281828, and so most people think, oh, it might repeat forever and ever in that pattern. No, it doesn't. It's like pi. Just like when you say pi is 3.14159, so on and so forth. E is another number that's similar. They're actually called transcendental numbers, if you're looking for some fancy terminology. Meaning they don't have an algebraic solution, meaning they don't have a polynomial with, like, and I should say transcendental over the rationals. You don't have a polynomial with integer or rational coefficients that solve that. That's where that comes from. So in this equation, we want natural log of 323, and then I just hit divided by natural log of 7, and I hit enter, and what do you know? We get some number that was real close to 3. Oh, well, holy mackerel. Disappeared on me. So we get 2 point, and I'll round it, we'll say 4 decimal places is what a 2.9691. And you could test it out with your own calculator, see what happens. So hopefully that makes sense. Now I just want to verify we could have done all these other problems with the same sort of change of base. So if you actually wanted to know one of those formulas that could work in all components, log base 3 of 81. So that would be natural log of 81 divided by the natural log of 3, right? You actually, and I could show you, there's another method you could do it without that. You could use a power rule as well, but I'll kind of show you with a calculator how we can do that. So just to let you see that even though these numbers can be nasty, like a natural log of 81, but as soon as we divide by the natural log of 3, those things cancel out and you're left with 4. So see how we match that answer. So really the big one is the change of base formula that can do all of them for you in terms of evaluating logarithms. But it's nice to know all the other properties. You can cut down on your time and not have to use a calculator, and you can start to do them. Whoops, sorry, I didn't mean to go there. It gives you a way to kind of go about doing things. So make sure you know those formulas, that and the change of base. And especially, I'd say this one up top is pretty good to know. And obviously the change of base, and then a couple of those properties, but this is one of a few law of logarithms that you might want to be aware of. It's extremely beneficial. Along with other laws of logarithms, actually, let me kind of write those down. Another law of logarithms, if you have a log base b of x times y, that's a log base b of x plus a log base b of y. And then if you have a log base b of x raised to the y, you can bring that power on down, y times log base b of x. And those work wonders for you. So Charlotte, let me know if this is kind of the problem you're looking for. So if you have a log base 3 of x plus 7 minus log base 3 of x minus 4 equals 2, we're going to use that other law of logarithms. So log base b of, oops, that's a b, of x minus log base b of y equals log base b of x over y. But so notice, this is where the minus sign occurs, so this is going to be combined into a single logarithm since our bases are the same. And that second portion is going to be down on the denominator. So we have log of 3 of, so x plus 7 goes up top in this single logarithm, and x minus 4 goes down below, and that thing equals 2. Okay, so now where the heck do we go from here, right? So if you're looking, we need to use that property of logarithms again, where we have the log base b of x equals y. That means that b to the y equals x, because what is our base? Our base is 3 and our y value is 2. So, but instead of x, we have something crazy on the inside. So you have 3 squared equals x plus 7 all over x minus 4. So hopefully everyone sees where that came from. If not, I mean, all it was, I was just using the definition of a logarithm. Make sure you can do that. This is the big property to know, because that's how logarithms are defined. If you don't understand that, you don't understand logarithms whatsoever, right? And so that's what we're trying to make happen, is kind of make sure that we can go from there. Now, moving forward from this part, notice that means 9. And if we want to get rid of the denominator, remember we multiply both sides by it. Just make sure you put it in parentheses. 9 times the quantity x minus 4 equals x plus 7. So that means 9x minus 36 equals x plus 7. Add the x or subtract the x over to the left hand side, that means 8x, and then you add the 36 over to the other side, that means we get 43. And then we get x equals 43 over 8. Okay, so yes, this is it. I'm confused at the point where multiply the 2. So we actually aren't multiplying the 2. We're moving it to the exponent. And the whole, I'm glad you're asking that question. The whole trick is logarithms and exponentials are inverse functions. So if you have f of x equals some b to the x, the inverse function of this is log base b of x. Right? Those two go hand in hand. Okay, so how do we move it to the denominator, right? So all I'm using, so how do we move it to the denominator? You see how it's a minus, a difference of the logarithms? So this is called, it's given a special name, it's called the quotient rule of logarithms. So don't confuse that. If you look up quotient rule, there's also a quotient rule in calculus that you do, which is, it has a different meaning in that case. So you got to know the context. This one is called the power rule, and the top one is called the product rule. And why are each of these given the names? So first off, the product rule. Log base b of x y equals log base b of x plus log base b of y. So if you look at the right hand side, you take this sum, and what do we turn it into? We turn it into a single logarithm that's a product, right? But so notice we take an addition and turn it into multiplication. So if addition becomes multiplication, think about what's the opposite of addition? Well, it's subtraction, and that's what you're seeing down here at the quotient rule. So you're seeing the subtraction. And so what does subtraction become? It becomes division. And that's the whole idea here. That's all there is to it. And if you don't believe me, that's fine. That's good. What we want to do. So let's take a look at some examples. Well, here, let me write it. I'll just shorten this up. If I do the log base 2 of 2 plus the log base 2 of 4. Notice that should be, and this is 2 squared, so this would be 1 plus 2, just by that property I had on the previous page. But let's see, and I'll put a question mark here, what's the log base 2 of 8? Well, 8 is 2 cubed, so notice this 1 plus 2, and that equals 3. And I can start checking these with all their numbers, and what's going to happen is every single check that you do, regardless of how you do it, you actually get the same answer. And where does that come from? Well, the way the logarithms are behaving, you've got to understand some exponents, what's happening there. So if I had b to the x times b to the y, notice that that's becoming b to the x plus y. It's part of this relationship right here that is causing what's happening with this behavior of exponents, because that's what the logarithms are, the inverse of the exponential function. So that's where all that stuff is coming from. So hopefully that makes sense. And then in terms of the quotient rule, why does it become a quotient? Well, once again, if addition becomes a product under the product rule, under the quotient rules, that subtraction becomes a quotient. So this was the numerator, so I'll write numerator, and the reason why is because it's a plus in front, and then since there's a minus, that means that part has to be the denominator in a single logarithm. Notice we don't have two logarithms anymore. Okay, so hopefully that makes sense on that part. If not, let me know. We can clear up the air a little bit more and kind of go through some examples. And the biggest thing, bust out your calculator and you can start to see. Try plugging in numbers, pick some bases. Try natural log of 15 minus natural log of, say, 7. And then see natural log of 15 divided by 7. See what happens. Test it out, right? You have a calculator there. You can work a lot of those out. So at the end of the day, we get x equals 43 over 8 on this, but that isn't quite all that's left. You need to check the domain, and in this case it isn't going to be too bad, because you get a logarithm is only defined when x is on the inside, so is greater than 0. So we need x plus 7 greater than 0. That means x greater than negative 7. Then we need x minus 4 greater than 0, so that means x is greater than 4. Luckily, 4 is only, so x greater than 4 is our worst case scenario, and x equals 43 over 8 is greater than 4, because 32 over 8 is actually 4, right? So this thing is a solution. That's something you're going to have to check, though. Sometimes you can get extraneous solutions from time to time. So hopefully that makes sense on that one. Now moving forward to the exponential side of things, there's a couple ways to solve this. We can use the power rule, can do some tricks for us, and then also there's an easier way because just this one happens to line up nicely. 8 and 4, if you notice, we could write those as powers of 2. So you could write the first one as 2 cubed, there's the 2x minus 6, and the second one is just 2 squared. And then we have that's raised to the, oops, started writing a 6, and then there we go, 6x minus 2. So properties of exponents, you can actually multiply those exponents on out. So you get 2, and then you get 3 times 2x minus 6 equals 2 times 6x minus 2. So these things are one-to-one functions, hence they have an inverse. So you have 3 times 2x minus 6 equals 2 times 6x minus 2. And so that makes 6x minus 18 equals 12x minus 4. Okay, so now where do we go from here? Well, you can go, you could subtract the 12 from, or subtract the 6x on the left hand side from both sides, and then you can add 4 to both sides. So you get negative 14 equals 6x. And so x equals, this is negative 14 over 6. Okay, so let's take a look. There's actually another method to solving this thing, and it involves the power rule. So just in case you didn't have things line up nicely, what you could do to bring the powers down, you could take a natural log of both sides. So natural log of 8 to the 2x minus 6 equals natural log of 4 to the 6x minus 2. And let me put it there, technically. Right there. What that allows us to do, this power rule right here, allows us to bring that out in front. This might be a bit more tedious for some of you, but it works if you don't have things match up in terms of the powers. So this can be a little bit more general. Oh, and by the way, negative 14 over 6 is negative 7/3 essentially. So you'll see another way to do that. Yeah, and so from this way we can go 2x natural log of 8 minus 6 natural log of 8 equals 6x natural log of 4 minus 2 natural log of 4. Right? So now it's a whole matter of, you got x's are a linear factor, and so there's one, there's another. You want to get them on the same side, and then everything that's not, get on the other side. So we'll move this on over to here, and we'll move this one on over to here. So at the end of the day, what do we have? We have 2 natural log of 4 minus the 6 natural log of 8 equals 6x natural log of 4 and then minus 2x natural log of 8. So notice the left hand side, you have the 2 natural log of 4 minus 6 natural log of 8. But on the right hand side, you can factor out the x and you get x times 6 natural log of 4 minus 2 natural log of 8. So where does this thing go? You could solve for x. Divide both sides by what that junk is on the one side, on the right hand side. So we're left with 2 natural log of 4 minus 6 natural log of 8 all over 6 natural log of 4 minus 2 natural log of 8. Okay, so a lot of you might not think that's the same thing, right? And that's good if you don't. I'm going to try and illustrate that it is. So first things first, we need to see is negative 14 over 6, right? And just so you can see it written as a decimal, you have it right there. And if you ever needed to, you could type that in. Now, for the next part, it's going to be a little bit trickier. You get 2 natural log of 4 minus 6 natural log of 8. Close the parentheses for the numerator, and now I need to start a parentheses for the denominator. 6 natural log of 4, and then minus 2 natural log of 8. So look, at these numbers look very different, and if I've done this correctly, hopefully I punched it in correctly, notice I get the same exact answer right here and here, right? That's the beautiful thing. I mean, you have two different ways to approach the same problem and come up with the same answer, right? So really kind of fun stuff that the logarithms allow you to do. So hopefully that makes sense in terms of what can happen. And then the second case is just a lot more general in terms of it allows us to solve these problems regardless. Okay. So if there's more questions on that, please let me know. Otherwise, we'll move on to the big finale here, compounding. So this is investing. This is where a lot of fun happens. So we have Joanna's deciding to invest in a series of CDs with different compounding times listed below. If Joanna wants to invest $11,000 into a CD with a 3.75% annual interest rate, then compute the amount she would have after 10 years with for the different compounding times. So we have compounded quarterly, compounded monthly, and compounded continuously. So in general, most of them are compounding times like this. So A of t equals P times 1 plus R over N raised to the NT power. In this case, P is the initial investment. R is the annual interest rate as a decimal. N is the number of times compounded per year. T is the time in years. And A of t is the final amount. Okay, So compounded quarterly. Here's what we have. Notice our principal, P equals 11,000. That's not going to change at all. Our R equals 3.75%. This is the tricky part for a lot of people. That's 0.0375. Got to convert it to a decimal. Our T, we're going to have that thing equals, we'll plug it in soon enough, but for right now, we'll have a general formula. So what happens is, when we're compounding quarterly, what that means is n equals 4. Okay, so your general formula without plugging in T is 11,000 times 1 plus 0.0375 all over 4 raised to the 4t. But what we want in particular is a of t, or a of 10. So that's 11,000 1 plus 0.0375 divided by 4 raised to the 4 times 10. And now here's where you need a calculator, and hopefully you could see how you have to be a little bit careful here. So what I would recommend a lot of times is writing this as 40, just because it's going to be easier when you're punching things in. So now we got to punch in the 11,000. Oops. And then we have to hit the 1 plus. Luckily, order of operations are in play when you're using a calculator, so as long as you're in good shape there. 0.0375 divided by 4. And then this is raised to the 40th power. But I'm just going to show you, in case you didn't do that, here's what you have to do. You need to put the exponent in parentheses. So you have to put 4 times 10, because what's going to happen if you don't put it in parentheses, calculators use the order of operations. So just raise it to the 4th power, then it multiply by 10. So at the end of the day, and think about your answer, this should be growing. Our investment should be growing, so we should get a larger answer. And we do, in fact, and we'll round to the nearest cent in this case, so $15,976.97. Is our final answer. So now, what should happen if we compound more often, compound monthly? Well, in that case, we get a new a of t function, and you get 11,000 1 plus 0.0375 over 12 raised to the 12t. And so that means that a of 10, because we're looking at 10 for our time in this case, is 11,000 1 plus 0.0375 divided by 12, and then we have 12 in 10 there. So once again, my recommendation is to just push in 120. That'll be a lot easier, but I'll do it the hard way. Oops. So we take 11,000. Make sure you put your parentheses. 1 plus 0.0375 divided by 12. Raise it to the power, and then we have a 12. Whoops. Sorry about that. I said I was going to do it the long way. So we'll do 12 times 10. Make sure it's in parentheses up in that exponent. That's the biggest mistake I see people make when it comes to this. So once again, make sure you do that. And notice we risen our amount to $15,995.55. So $15,995.55. Was it 55 or 95? Yeah, 55. So we rose a little bit more. So now the real question is, what do we do when we're compounding continuously? Can anyone tell me the formula for that scenario? When we compound continuously, what's the new formula? Do we use the same thing as n? Just how do we do that? What actually happens? That's right. So compound continuously. It becomes, yeah, it is a different formula, and it's that A of t equals P times e to the RT power. The biggest word you always look for is continuously after that compounded. If it says continuously, that's when you use, I call it the PERT formula, right? So in this case, notice there's no more n, okay? And the reason why you're compounding continuously, your n is essentially gone to infinity, and this is the formula that pops out. So this formula is 11,000. E, which is just that number, 2.71828, so on and so forth. R is that 0.0375. Then we have a T. Yeah, so there's a question, are there any problems where we need to find the principal? I can go through that real quick. That's not a problem. So in this case, I'll finish this one off. We have A of 10 is 11,000. E to the 0.0375. And then we want 10 up here. Okay? So now, what does this become? So make sure you know where to locate this button on your calculator too for the E button. How do we do it? Oh, crud. So we hit second, and it's right above the natural log. You see that e to the x sitting right there? So you have e to the, and then it's making sure everything is in parentheses, 0.0375 times 10. Hit enter, and we get our final answer, $16,004.91. Okay, so the big deal is if all things are given equal, right, the rates and all that stuff, you just want it to be compounded more often. Now, is it a big jump? Well, no, not really. I mean, if you look, we had a bigger jump from quarterly to monthly, but going from monthly to continuously, there wasn't as big of a jump, it seems. Right, there was 20 bucks going one way, and then what, an extra 9 bucks about going the next. Okay, so make sure though that you're aware of the different formulas. So you had two formulas here. You had the compounded and you had the compounded continuously. So I see a question about, are there any problems where we need to find the principal? I'm happy to go through one real quick. Just let me know, would you rather have it be compounding using the continuously case or compounded using the like quarterly or monthly? You come up with a scenario and I'll kind of go through the question. I'm going to erase this real quick and just kind of build off of this part for that question. So let me know your preference. Quarterly or monthly? Okay, so that sounds good. I'll go with quarterly. So I'm going to erase all this. I'm assuming you all have that. So let's try a problem where we're finding the principal. How do we word that? So I'm going to still use Joanna just to save myself some time with the setup. So you still have the same formula, and we'll use that. And so let's see how we create one of those. Okay, Joanna has decided to invest in a series of CDs listed below. If Joanna wants rather than a series of CDs, I'm going to have Joanna wants to invest in a CD. So yeah, and Joanna's deciding to invest in a CD. Well, so Joanna wants to invest in a CD with let's do it this way, where she will have $20,000 after, let's say, we'll use 15 years this time. If Joanna selects a CD that is compounded quarterly, with a 3.75% annual interest rate, then compute the amount she would have to initially invest in order to have $20,000 after 15 years. Okay. So what's the dead giveaway? Well, it's kind of the ringer to tell you that you're looking for the principal. Compute, right, or find, or determine, or whatever the case it is, the amount she would have to initially invest. Okay, saying we're looking for initial investment. So that means when we have that formula, A of t equals P times 1 plus R over N raised to the NT, we're looking for this P value. Okay, so we have A of t. The final amount that we're looking for is $20,000. Now, other ways you can hear this worded too. There's little twists on this all the time, but boils down to the same type of problem. So say Joanna wanted a car that's worth $27,000 and she only has such and such amount, you know, what would she have to invest in order to get to that amount after so much time? There's other variations on this question. You'd have to use logarithms if you're trying to find the amount of time you need to have the money invested for, if you're given the interest rate and all that stuff. There's all sorts of different variations, but they boil down to just reading to where you need to find that. What are you trying to find, right? So in this case, P is going to be our missing value, but our R stays the same. I didn't change that at all, but I did change in this problem the N. So N in this case is, where do we do it? Compounded quarterly. That's what you all selected. So 4 goes down there, and then 4 goes up here, and then our time is 15 years. Okay, so this looks scary, right? But all of this junk is a number. Since it's a number, we can divide by that number. So you have 20,000 divided by that whole junk, right? So 0.0375 divided by 4 raised to the 4 raised to the 15th. That equals P. So I'll just move P to this side. And then how do we figure out our answer? Well, we bring out our trusty calculator once again. You'll notice that this is our friend when it comes to these type of problems. Let me clear that out. I don't need that stuff anymore. So if we do 20,000, and obviously you could do a kind of a quick check. Should this be more or less than 20,000? Well, I sure hope it's less, right? Otherwise, you don't want to be investing in that investment if you're losing money. So kind of keep that in mind. Do the common sense check with a lot of these things. So first off, we're going to put the whole denominator in parentheses, and I'm actually going to toss in another parentheses just so I can put the 1 plus 0.0375, so on and so forth. Because I want to even include the exponent in the inside the parentheses. So 0.0375 divided by 4 and then we have to raise that to the, once again, I could just make it 60. That would be easier on myself, but I'll do it the hard way. I'm putting in parentheses for that exponent. I can't emphasize that enough. That's the biggest mistake I see, and people are way off on values. And then I'm going to close off the parentheses for the whole denominator. So that's the other problem, is people forget parentheses in the denominator. Okay, so I hit enter, and notice there's our initial amount, $11,425.56. So $11,425.56. And that's all that we had to invest initially. So, and that's how you go about it. All of them pretty much follow the same routine. I could do something where I said how long would it take for Joanna's investment to double and things like that. That's also other variations of this stuff. So, but hopefully that makes sense with all these. I'm glad you were all asking questions. It's good stuff. So, and best of luck coming up on the midterm. If you have any questions in the meantime, there's discussion boards and stuff. Please make sure to post those questions. So, have a good one. Enjoy the rest of your night.